So we're going to cover the third and fourth sections of Chapter 10 today. We're going to talk about exothermic and endothermic processes as well as thermodynamics in general. So let's take a look at endo and exothermic reactions and processes. First of all, let's start with some basic definitions. A system is part of the universe that we wish to focus our attention. So if this were the reaction we're taking in chemistry class and we're looking at it and wanting to look at what's going on with this reaction, that would be our system. Then everything else in the universe is considered the surroundings. So we're going to look at energy flow into and out of the system. Energy change accompanying a burning match. So you've done this so many times to light your Bunsen burners, and you know that if we look at the match itself, let me grab a pen here. If we look at the potential energy here in the match, we know that the highest potential energy is right here at the beginning before you actually light the match. And in this case, this is our reactant, is the match. That's considered the system. Everything else is the surroundings. So if you can keep that in mind as we go through this, it may help. So we light the match. So what happens in the potential energy? The potential energy in this match head is then reduced because energy has been released to the surroundings and it's released as heat, which is the fire that allows us to light our Bunsen burner. So when the reaction is completed, the products that we have a lower potential energy than it did to start with, and the reason for that is because even though the system has gone through a change, something happened to the surroundings as well, and in this case, heat has been given off. So that would be considered an exothermic reaction. Let's take a look now at this equation that they're going to ask us to do some problems using today. So delta E in this case is the change in energy. That's what delta means, change in, so that's what that is, energy. Q is heat, and W is work. So in our system, if heat is put into the system, the Q value is going to be positive because it's added to the system. If heat is transferred out of the system, our Q value is going to become negative. If work transfers into the system, W is going to be positive, and if it's out of the system, it's going to be negative. And that's just a really easy relationship to keep in mind. Our overall energy and change in energy is going to equal the amount of heat as well as the amount of work done to that system. So an endothermic process, heat flows into the system, endo. It absorbs energy from the surroundings. In an exothermic process, on the other hand, energy is going to flow out of the system, and the energy gained by the surroundings must be equal to the energy lost by the system, because we've already talked about the law of conservation of energy that says energy cannot be created or destroyed, only changed in form. So if it's gained by the surroundings, it must be equal to what's lost by the system. Okay, so let's look at a concept check. Is the freezing of water endothermic or exothermic process? And let's go back and see, just by definition again. An endothermic process is a process where heat flows into a system and heat is absorbed from the surroundings. Exothermic process, energy flows out of the system. So let's go ahead and go back to our question again. So is the freezing of water endothermic or exothermic? Is energy taken in or is energy given off? Correct answer is exothermic. And it's exothermic because the process that we're dealing with, the freezing of the water, you have to remove energy in order to slow the molecules down to form a solid. So whether you realize it or not, as water is freezing, it actually is giving off energy to its surroundings. Let's look at the next question. We're going to look at 5 examples, and we're going to classify them as either an exothermic reaction or an endothermic reaction, and I'll explain on each one. So, your hand gets cold when you touch the ice. Is that endothermic or exothermic? It's an exothermic reaction because the heat energy is going to leave your hand and go to the ice. The ice gets warmer when you touch it. Is that endothermic or exothermic? That is an endothermic reaction because the heat flows into the ice from your hand. So it's considered an endothermic reaction. Water boils in a kettle that's heated on the stove. Is that endothermic or exothermic? That's considered endothermic as well because the heat energy flows into the water to boil it, goes into the system. What about water vapor condensing on a cold pipe? That's considered an exothermic reaction because the heat energy leaves to condense the water from a gas to a liquid. And the last one, ice cream melting. That's an endothermic reaction because the heat energy flows into the ice cream and melts it. All right, let's take another look at a concept check. It says for each of the following, we need to define a system and its surroundings and give the direction of the energy transfer. All right, so let's look at the first one. Methane is burning in a Bunsen burner in a laboratory. Okay, so I just inserted a picture here of a Bunsen burner so you get that in your mind. So you're in the lab and you have methane burning in a Bunsen burner in the lab. So we want to know what is the system, what is the surroundings, and the direction of energy transfer. All right, so we're looking at this picture. The system is going to be the methane, which is CH4, and the O2, and the carbon dioxide that it's producing, and the water vapor that it's producing. These are all parts of the system. The surroundings, everything else around it. So here's our system with the flame, with the methane, the oxygen, the carbon dioxide given off, and the water vapor given off. And the surroundings are all this. Everything else around here are the surroundings. So the other question was, what's the direction of energy transfer? And we know that that's going to be hot and it's going to give off heat, and energy is going to be transferred from the system to the surroundings. All right, let's take a look at the second example. Water drops sitting on your skin after swimming. So here's a little girl in her swimming pool, and right through here, on her arms, on her face, we're going to pretend like there's water because she was just in the water, and now she has water on her skin, and it's going to evaporate. So the question, again, that you need to ask yourself is, what is my system, what is my surroundings, and what direction will the energy transfer? Let's go to blue since it's water. So in this case, our system is going to be the water drops on her skin. So let me just do this. We're going to draw some water drops on her skin to get a visual. Okay, so there's water drops. So the system is the water on the skin. What's the surroundings then? The surroundings are everything else. So all this, including the little girl, including her skin. Okay, and I need to draw through her face, but we're going to do that. Okay, so everything else besides the water drops is considered part of the surroundings. Now, what's the direction of energy transfer? Well, energy is going to be transferred from her skin to the water. So, from her skin to the water. So, in this case, because the surroundings includes her body, the system, the water drops, this is actually an endothermic reaction, whereas the burning of the methane, which gave off heat to the surroundings, is an exothermic reaction. In this case, the surroundings are giving heat to the system, which are the water drops, making this an endothermic reaction. And the final example for this section 10.3, the question is, looking at this reaction, hydrogen gas and oxygen gas react violently to form water, which is lower in energy, a mixture of the hydrogen and oxygen gas or the water, and explain. Okay, so in this reaction, we have hydrogen gas and oxygen gas reacting together, giving off a violent reaction, which is probably going to be heat to form water. So the energy that was contained within these bonds is going to give off part of its energy to the surroundings. So it should make sense then that the water has a lower amount of energy in it than what the reactants did. And as you can see in the result of this, that water does have the lower energy. The next section we're going to take a look at is over thermodynamics, and it's section 10.4, and we've covered a few of these things back in 10.3, but let's go ahead and talk about them again. Thermodynamics, by definition, is the study of energy, and the law of conservation of energy is oftentimes referred to as the first law of thermodynamics, that energy cannot be created or destroyed, but only change in form, and this assumes that the energy of the universe is held constant. Internal energy, big E of a system, is the sum of the kinetic energy plus the potential energy of all the particles in the system. And to change the internal energy, we use the formula delta E equals heat, which is Q, and W, which is work. The sign is going to reflect the system's point of view, and this is probably the most important thing for you to remember. That when we talk about the sign, we're talking about the system's point of view. An endothermic process, we're going to have Q being positive because energy is going to be put into the system. In an exothermic process, Q is going to be negative because it's the system's point of view and energy is going to be given off by the system. So here's a diagram showing that the surroundings in the system, when we give off energy, energy is going to be negative, and when we put energy into the system, it's going to be positive. And here's just a diagram of the reaction that we talked about earlier, or the equation we talked about earlier as we started section 10.3. Let's look at internal energy. Sign's going to reflect the system's point of view. The system does work on the surroundings, then W, or work, is going to be negative. The surroundings do work on the system, W is going to be positive. The directions on how to do the problems in this section are pretty easy. Just remember that you're going to use the formula delta E is equal to Q plus W. Refer back to the notes if you need to in order to answer your questions correctly.